Chapter 3, Polynomial and Rational Functions, Section 3.2, Polynomial Functions. This section provides an introduction to some of the general characteristics of polynomial functions. There's a lot to read, so I'll just be reading through this with you and adding things, additional explanations and so on as we move through the notes. We begin with the basic definition of a polynomial function, which looks rather complicated but is not as bad as it might look. A polynomial function of degree n has the form f of x equals an x to the n plus an minus 1 x to the n minus 1, etc., plus a2x squared plus a1x plus a0, where n is a non-negative integer. So one thing we don't see with polynomial functions are negative exponents. And the an's, an minus 1, etc., are real numbers which are called coefficients. The term an x to the n, assuming that an is not equal to 0, is called the leading term of the polynomial. The leading term is associated with the highest power of x in the polynomial. A0 is called the constant term. Here again we'd be assuming if there's a constant term that it's a non-zero value of A0. With an called the leading coefficient. So the coefficients are the numbers in front of the powers of x. The number in front of the highest power of x, which often occurs as the first term of the polynomial, is called the leading coefficient. And let's see, did we define degree here? Yes, the degree of the polynomial is the highest power of x within the polynomial. Here's a specific example. F of x equals 2x cubed minus 3x squared plus x minus 4 is a polynomial function of degree 3 because the highest power of x is 3. It's also called a cubic polynomial since the degree is 3. This function could be expressed in the notation above as a3x cubed plus a2x squared plus a1x plus a0, and a3, a2, a1, and a0 would just be the coefficients, the numbers in front of the powers of x, that is 2, negative 3, 1, that's the third term can be thought of as 1x, and the constant term here is negative 4. Now certainly polynomial functions are frequently encountered as you go through algebra. So you're already familiar with some types of polynomial functions, and these have already been discussed in some of the sections we've covered. First of all, constant functions, mentioned in section 2.6, have the form f of x equals b, or y equals b, where b is a constant, a number, and have graphs that are horizontal lines. These functions can be classified as a set of zero-degree polynomial functions. That is, something of the form f of x equals a0 or a0 x to the 0 being equal to 1. So these are classified as zero-degree polynomial functions. So there's no x that occurs within the function. Note that the constant function f of x equals 0 is a special case that's considered to have no degree. F of x equals 0 or y equals 0 would be the equation of the x-axis, by the way. The next step up would be linear functions. This is discussed in detail in section 2.3, which is prerequisite material for the course. These functions have the form f of x equals mx plus b or y equals mx plus b, and the graphs are straight lines. Functions can be classified as the set of first-degree polynomial functions, the highest power of x being x to the first, with general form f of x equals a1x plus a0. So we can write it in this more general form rather than in the form mx plus b, but it means the same thing. Note that the constant functions are also considered to be linear functions with m equal to 0. So we can actually classify the constant functions under the linear functions as a type of linear function, since constant functions also have graphs that are straight lines, albeit horizontal lines. So constant functions are linear functions with slope of 0, m is equal to 0. And then the third type, the quadratic functions, which were studied in the previous section, f of x equals ax squared plus bx plus c, whose graphs are parabolas. These can be classified as second-degree polynomial functions, and their general form could also be expressed as f of x equals a2x squared plus a1x plus a0. So normally we use a, b, and c, but we could also represent it this way. Now, all of the functions that we've described above, when we think about their graphs and so on, demonstrate three properties that are common to all polynomial functions. First of all, their domains are the set of all real numbers. They have unrestricted domains. We don't worry about division by 0, for example, or negative numbers under square roots or anything of that sort. Second property, they are continuous, meaning their graphs have no breaks of any kind. No breaks, no holes, no jumps in their graphs. And thirdly, their graphs are smooth, meaning they have no abrupt turning points. So you see below a typical polynomial function that is likely a third-degree polynomial function there. You see it's continuous, it doesn't have any holes or breaks of any type, and wherever it turns in a smooth fashion. The second graph is the graph of what's called a rational function. These are actually related to polynomial functions, but a separate family of functions. This is not a polynomial function because we can see breaks in the graph. There's three different pieces to the graph. We do not see this with polynomial functions. So we have two discontinuities, two values of x at which there's a discontinuity in the graph. So that's not a polynomial, the graph of a polynomial function. And then the third example is an example of a function that likely has a radical expression. And notice that at x equals 0, there's an abrupt turning point. It's not a smooth turn, it's a sharp turn in the graph located right here. And we don't see this kind of behavior with polynomial functions. When we have a turning point, such as here, it's a smooth turning point. So graphs of polynomial functions are continuous and smooth. One way to determine the behavior of the graph of a polynomial function is by looking at its leading term. The degree and leading coefficient of a polynomial function determines the far left and far right behavior or end behavior of the graph. So the leading term of a polynomial function, the term associated with the highest power of x, affects how the graph eventually behaves to the left and to the right. Here is the statement of the leading term test, which will sound like quite a bit to remember, but I'm going to give you a method of remembering the various cases of the test to make it a little bit easier. The leading term test says given f of x equals an x to the n plus etc. etc. This is a degree n polynomial with leading coefficient a sub n. The graph of f eventually rises to the left and to the right if n is even and a sub n, the leading coefficient, is positive. So if we have even degree and a positive leading coefficient, the graph of f eventually will rise to the left and rise to the right. Number 2, the graph falls to the left and to the right if n is even and an is negative. That is, if the degree is even and the leading coefficient is negative, then the graph eventually falls to the left and falls to the right. Number 3, the graph falls to the left and rises to the right if n is odd and an is positive. That is, if the degree is odd and the leading coefficient is positive, the graph eventually falls to the left and rises to the right. And the number 4, the graph rises to the left and falls to the right if n is odd and an is negative. That is, if the degree is odd and the leading coefficient is negative, the graph eventually rises to the left and falls to the right. The best way to remember the leading term test is to remember some familiar examples. And so let's turn to two functions we encountered early in chapter 2 when we were talking about a library of basic function types, the squaring function and the cubing function. The squaring function will illustrate the cases numbers 1 and 2, where the degree of the polynomial is even. And the cubing function will illustrate cases 3 and 4, where the degree of the polynomial is odd. So if we consider the case of an even degree and a positive leading coefficient, we can remember the behavior of the graph of f of x equals x squared. And I've written that as 1x squared to emphasize the fact that the leading coefficient here is positive 1. The degree is even. The degree is 2. Notice it's a parabola. We know this parabola rises to the left and rises to the right. So it turns out that any polynomial function with even degree and positive leading coefficient will eventually also rise to the left and rise to the right, just like the parabola would. Case number 2 is illustrated by f of x equals minus 1x squared, or just minus x squared. We would know that this is a parabola with vertex at the origin that opens down. We have a reflection occurring here. And notice to the left and to the right, the graph falls. Any polynomial function with even degree and a negative leading coefficient will do the same eventually to the left and to the right. It may not be a parabola, but to the left and to the right, eventually the graph will fall in both directions, just like the parabola does. For f of x equals x cubed, or 1x cubed, we have case 3, odd degree, positive leading coefficient. Notice that the graph of the cubing function eventually falls to the left and rises to the right. Any odd degree polynomial function with a positive leading coefficient to the left and to the right will eventually do the same. And then if we have minus 1x cubed, the graph gets flipped across the x-axis, and we see that the graph rises to the left and falls to the right. Sometimes what we can do is put arrows in. So rises to the left, rises to the right. It's like this. Falls to the left, falls to the right. Here's falls to the left, rises to the right, rises to the left, falls to the right. Now, the graph, depending on the type of function, may have other features. For example, if we look at this last one, it might have more turns. It might do something like that. But eventually, the left and right-hand behavior will be the same as the simpler function, in this case, minus 1x cubed. So we can use these simpler functions to remember these 4 cases. And this makes it much easier to remember the leading term test. We'll continue with example 1 in the next video.